Question 1. A 9-volt cell has an internal resistance of 12 ohms. Calculate the potential difference across its terminals when it's supplying a current of 50 milliamps. So, as always, it's usually a good idea to draw a little diagram to help ourselves. Presumably there is some more resistance in this circuit, so my diagram should probably include a second unknown resistor. We've got our internal resistance, which is 12 ohms, and our EMF of 9.0 volts, and we're told that the current is 50 milliamps. So we'll put that in as times 10 to the minus 3. That's the EMF we've written there. So in this, we're trying to find the terminal potential difference. So across its terminals, we'll have its EMF minus the internal resistance times the current. This is sometimes called the lost volts in the cell. So in this particular case, this is 9.0 minus 50 times 10 to the minus 3 multiplied by its internal resistance, which is 12.0. So that gives us a value of 8.4 volts. B, determine the maximum current this cell could supply. So this will happen when the external resistance is as low as possible. So when the external resistance is 0. At this point then we will get that the current is just equal to the EMF over the internal resistance. So that is 9.0 over 12, which is 0.75 amps. Draw a sketch graph to show how the terminal potential difference varies with the current supplied if the internal resistance remains constant. So again, the key idea is spotting this, that V is equal to the EMF minus the internal resistance times the current. So if I plot a graph of terminal potential difference, that's V, against the current, I don't need to put it there, that's I, then effectively I just need to do a slight rearrangement on this equation to minus R times I plus E. Now what this means is that if I put V on my y-axis and X on my y-axis, I expect the gradient to be minus R and the intercept to be E. So I should have a straight line, that's not a very straight line, close enough, a straight line that goes through a value here which gives the EMF of the cell, and the gradient of this, delta y over delta x, should be equal to minus the internal resistance, which is why we've got a negative gradient. Let's just label this. And that covers part D as well.